Hi, this is Yousef Alnajjar. This is the final for ME 304. We're given the question for the beam shown loaded below. Find the principal stresses and the maximum shear stress at point A. Point A is right there. Use the coordinate system shown, i.e. the x-axis is along the beam going through it. So going right through it. To find the principal stresses and the maximum shear stress with respect to point A, we want to first map out where these forces are respect to A, and then get the reaction forces we'd have there, as well as the moments we'd also find. So to do that, we'll start by just drawing a free body diagram of this. Here's a quick sketch. Go. Okay, we'll call this, we'll call this A. This is A. And now what we're gonna do is basically just whatever force that is acting with respect to each axis, we will map out the reaction force, which would be in the opposite direction. So for the moment over here on the X, it would be 10 kilonewtons to the right, so ours would be towards the left. So there's Rx, Ry, same thing. And then Rz. Again, all of these reaction forces are just the opposite of whatever force is acting on the beam. Now, there would also be moments at each force acting in each axis. Same thing. So now we have 6 properties basically. And now what we're trying to do is we want to find out where these forces are with respect to point A. And to do that, we're going to use matrices to find the moments at these at point A, as well as the reaction forces. So we'll just write our load over here. It's going to be in newtons, and we're going to convert this 10 kilonewtons into newtons just because it's easier. So we'll have a 10,000. We will have a 750 in the Y over here, and then we will have a 500 in the Z. And now we're going to have our R vector, or position vector, with respect to I, J, and K. We will have our force vector, also with respect to I, J, and K. And finally, we'll have our moment vector, which is just the cross product of R and F. And I'm gonna actually keep this in Newton millimeters because that can convert to megapascals easily. And that will also be in with respect to I, J, and K. Now we'll just go down the list and do this. So the 10,000 on the X direction is going to be 180 millimeters plus the 40 millimeters. So 220 millimeters. So let me just write millimeters. This is newtons. 222 millimeters in the X, 0 in the Y, 0 in the K, just because it is on the line of action. And then 750 is going to be this force over here. We can just see it's 180 millimeters away. It'll be right on the line. So that would be 0. That would be 180. And that's again because you need to move 180 millimeters in the X direction to get over here. And then 0, 0. And then the last force, 500, is going to be the same at 220. Oh, did I write 222? Sorry about that. It's 220. Now the forces are going to be with respect to I, J, and K as well. So the force in the X direction, we know it's going to be 10,000. And that's going to be working in the I. So here, 10,000. And then we'll have 0, 0, just to make it more clear. And then for the 750, we have it in the Y direction. So it's going to be 0. And then it's going to be negative 750 because it's acting against the axes. It's going upwards, the axes, and this force is coming downwards. So it's negative, and then 0 in the K. And then for the last one, oh, I am sorry, this is also 0 over here. And then for the K, we're going to have 0 over here in the I direction and 0 in the J direction. And then we're gonna have 500 going into the Z direction this way. Okay, now we want to solve for our moment vectors, so we do the cross product. So for this one over here, if we do the cross product of any, it just ends up being 0 all around. And that makes it much easier. And now let's do the 750 Newton force. So if we do I, that's 0. If we do the J will work. So now we have 180 times negative 750. That's going to be 0 in the I. And let me get my calculator. It's going to be negative 750 times 180. And that's negative 135, 5,000. So I'm just gonna write negative 135 times 10 to the third, and then 0 over here. And then finally, we can do this one over here, the 220 force. And that is going to be, I'm sorry, did I do something wrong here? The 180 is over here. Oh, my bad. This is in the K direction. 0, and then this is negative 135 times 10 to the third. And then over here it's going to be in the J direction. We cover the J's is 220 times 500. And that gives us 110,000. So that'd be 0, 110 times 10 to the third, and then 0. I know it's messy, but let's clean it up right down here. Let's do this. We'll have our reactions in the X, the reaction in the Y, the reaction in the Z, and then we will have our moment in the X, our moment in the Y, and our moment in the Z direction. So now for the reaction forces, basically the reaction force is going to be the opposite of whatever force it was there. So for over here, the force is 10,000 kilonewtons, so the reaction force would actually be negative 10,000 kilonewtons. And then for the RY, over here we have negative 750, it would just be 750. And then R of Z, over here we have 500, it becomes negative 500 newtons. M of X, there is no M of X at all, so that is 0. M of Y, we have 110 times 10 to the third Newton millimeters. Let's just get some water. And then in the Z direction over here, we have negative 135 times 10 to the third Newton millimeters. Now that we have all of this, we can start mapping out our reaction forces. And looking at this graph, we can tell what types of forces we're gonna get based on how it's acting on the beam. So in this case, our R of X is actually gonna be axial. The R of Y would be transverse. And so would R of Z. And that's just because Rx is acting on the direction, on the plane of where the point is, and it's not causing any torsion. Over here we have forces acting against it, so there'll be torsion force, torque force. So let's start solving for our R of X. So our R of X, we said, is axial. And we'll draw our little box over here. So right now we're gonna map it out as onto the Y and X axis over here. And over here we're just gonna be having 10,000 newtons coming out. So it's in tension, which is gonna be positive. And because it's in tension, so I'll just write T over here, we know that sigma X, because it's acting in the X direction, is gonna be equal to P over A, and that's gonna be equal to 10,000 newtons over, now what is the area? The area, we can get that from right over here. It's gonna be 32 by 60. So it'd be 32 times 60. This is millimeters. And we come out with sigma X equaling, let's do that, 10,000 over 32 times 60. That equals 5.21. And because it's in millimeters, we can just say that is megapascals, because it'll go to times 10 to the 6th. Now we draw the stress blocks. And we know it's going to be acting only on the X direction, so we're only going to be having two stress blocks. So it's going to be the XY and the XZ plane. And we're going to draw this. And we're going to have the force be coming out of the X direction, and that is 5.21 megapascals. And now for the moment of X, it's gonna actually just be 0, since we have nothing happening around that area. And this force is acting into the point, so there could be no moment. It's acting on that line of axis. We'll move on to R of Y, which we said is going to be transverse shear. Transverse. And we'll draw the the block again. And basically right here, what we're doing is we're just trying to map out where this point would be with respect to these axes. So, oops, this is the Y axis, and this is point A. So basically what I am doing is I'm taking the Y and X axis and I'm putting my face over here and looking that way. And if I'm looking that way, point A would actually be on top, and we would be having no force happening. And that is basically because when we flip it around and we look, so now we're gonna be looking at it from the top. Over here is the neutral axis, and it's up here. That's A. This is actually the outermost fiber, and that actually means therefore the area is equal to 0, meaning tau equals 0, and that's just because the equation is tau equals 3/2 times volume times area. And if area is equal to 0, this just goes away. And there is no shear force. But at the moment y, we're actually going to be having bending. And that is because at moment y, if we just like put our finger right here and you see it coming down, you'll see that it will basically be bending that point right there. So let's draw it from this side, this angle of the z and x axis. So let me draw the block. We'll have the x-axis coming out this way. It's the z. Oops, that's pretty bad. That's the z-axis. And we're going to be having point A actually be right there. And that is because if you're looking at the zx axis, it would be right smack in the middle of the x-axis. And now for sigma x, we're gonna go equals the moment around y, the moment y times the y over I. But since this is right on the neutral axis, y actually equals 0, and therefore there is no bending at my. And finally, RZ, again we said is transverse. That's because if we hold our finger at point A and it's coming in towards this way, we'll have bending this way. Let me just put this right here. Okay, transverse. So let's draw this with respect to the XZ plane. So we'll say Z is coming down this way, and X is right there. That will leave point A right there. If you're looking at it from the top, X will be right there in the middle. And if we want to flip it around and look at the end view, so we actually want to take this piece and flip it towards us, we're going to be seeing this point over here now on the neutral axis, and this will be on the neutral axis, and so then we can solve for tau of XZ plane equaling 3 volume over 2 times the area. And this V is going to be the 500 Newton force, since that's the one we have coming down over there at 500 newtons. So this is going to be equal to tau x z equals 3 times 500 over 2 times the area, which we said was 32 times 60, and that is going to equal 3 times 500 over 2 times 32 times 60, 0.391 megapascals. And on the stress blocks, also there were no stress blocks over here for our y because there were no reaction forces. And over here, basically, we know that this is going to be working in the xz plane, and the only other plane that we're working in is the rx, and we see that it's also working in the xz plane, so the entirety of the combined load will be working inside of the xz plane. And let me just look at okay. And this will be z x with a positive direction going this way. Since we know this is positive. Oh my goodness, I'm so sorry. This is positive, and this is at 0.391 megapascals right there. Now the moment at z is going to be bending as well. Again, let's draw this with respect to the x z plane, y plane, sorry. Because the bending's happening on the z. So if it's happening on the z, we're gonna be looking at it towards the y-axis to see what is happening. And that point would actually be up here in this case. So this is A right there. And we are having a torsional force of 135 times 10 to the third newtons. And in this case, we will be using sigma x equals mzy over I. The moment we know it to be 135 times 10 to the third newtons, millimeter times millimeter, sorry. And y is actually going to be, so if we're looking at this way towards this plane, the y and x, we know it's 16 millimeters from halfway up. So our y bar is going to be 16 millimeters. And then I is going to be 1/12. The base times the height. Our base is going to be 60. And the height is going to be 32. And that is cubed. And then altogether we get sigma x is equal to 135 times 10 to the third times 16, 1/12 times 60 times 32 to the third. And that leaves us with 13.18 megapascals. And since we know it's working in the x direction, we know the most it's gonna work in. We know it'll work in the y-x, but we don't really need to sketch this one, but I'll just do it anyway. So it would be 13.18 megapascals, but it will be mainly working in the zx. We're gonna have most of our stresses and shear force in this plane. And you'll see now why in the combined loading. So now we are going to combine everything. So combine. And basically to do that, we're gonna look at what we have and see which plane has the most amount of stresses and shear force acting on it. So over here we know it works in the y-axis and the zx axis of sigma x, but we also know Rx works in the XY and XZ axis. But what we're gonna wanna look at is actually this shear force, the 0.391. It's actually only working in the ZX axis, which means all our forces, the max, sigma 1, sigma 2, and our max shear force should come in the ZX axis. So we're going to combine all of it into one big block. Let's do ZX. And we are going to have an axial force of 5.21 megapascals in tension. Nothing over here. Nothing here. And 13.18 megapascals positive. So we're gonna add those two numbers together. So we're gonna add 13.18 plus 5.21, which equals 18.39 megapascals. And then for the shear, we only have this shear force acting in the positive direction. So coming over here, this, and then that's at 0.391 megapascals. And now we just solve using these equations. Sigma 2 equals sigma x plus sigma z in this case, since we're working in this direction, this plane, and then plus or minus the square root sigma x minus sigma z over 2 squared plus tau x z in this case squared. And we know this bad boy over here is gonna be equal to the tau max. So we can just write that down here. We'll do it right after actually. So we'll do sigma x, we know is 18.39 plus 0 over 2 plus or minus 18.39 minus 0 over 2 squared plus 0.391 squared. And from this, we are going to get 18.39 over 2, 9.195 plus or minus we'll do 18.39 over 2 squared plus 0.391 squared. 9.2. 9.20. So we know tau max equals 9.20 megapascals. And now sigma 1 is going to equal 9.195 plus 9.2, 18.4 megapascals. And then if we take these two and subtract them, we're left with negative 0.00831 megapascals, negative 0.00831 megapascals. And there we go. Thank you. Here's my signature.